Before we do, does anyone have any comments, questions, concerns about anything related to what we looked at yesterday? The last few went downhill. Is that a pun?
I guess it is.
Yes, it is.
So this is where we use
Last few went downhill. Okay, cool. Brad, pick one. Are they all the same? A student pulls 125 Newton object up a 25-degree incline. If the coefficient of friction is blah, of course, that's a good one. Fluffy the cat is morning. Fluffy the cat slides freely down the long porcelain cat slide. Don't really look cool. They give you the incline, the coefficient of friction. Ooh, 8's a good question too. 9, a trucker loses brakes at the bottom of a runoff road. Oh yeah, 7, 8, 9 are all good. Brad, pick one. Sure. Let's take a look at question number 7. So I've got some space down below, so I'll put it down there. Yeah. Okay, so a student pulls a 125 Newton object up a 25-degree incline. So let's draw that thing. There's our 25-degree incline. The box is moving up the incline, so let's draw it in the middle so I've got some space to work. He's pulling the object, or they are pulling the object up, so it's important. They're given a coefficient of friction. Mu is equal to 0.18. Okay, cool. What forces are acting on the block, Brad? Applied force which way? Going up. Okay, friction going against the applied force. Yeah, not up. Perpendicular to the surface. Okay, careful. Because this will be a question on either your final exam or on this unit test. There will be a question that says, what is the correct free body diagram? This is the correct free body diagram. Gravity straight down, friction down the incline, applied force up, normal force perpendicular. Free body diagram is done.
So those two, the perpendicular and parallel, go like the second.
Yeah, that's the next. They are the broken down pieces of gravity. They aren't individual. They aren't their own forces. They're just gravity broken up. So this is the free body diagram. And now we can add what you wanted to add. You said there was a FG perpendicular that is opposite the normal force. And I interrupted you. Carry on. And an FG parallel, we call it FG parallel because it's parallel to the incline. It goes down the incline. So the green ones I drew there are, the forces. The two blue ones I added are just this force broken up. And now we can start to add some stuff. What do we know? There's one. The object is 125 newtons. So that is FG. If they tell you that it's a 125 Newton object, that is the force of gravity acting on the object. If they said it was a 125 kilogram object, that would be the mass. You'd multiply that by 9.8. But so the units are important. That is FG. And so now we can, well, what can we do? There's a key phrase in the question that's going to dictate how we move forward here. We want to find the applied force. Before we do any of that, there's still something in the question, the wording of the question, that's going to tell us where to go. Yeah, sire. Constant velocity. Constant velocity implies what? Okay. So acceleration equals 0. If the acceleration equals 0, that means F net equals 0. And if the net force is equal to 0, what must be true? Well, we've got this guy acting up, we've got this guy acting down, and there's this guy acting down. There's 2 acting down, 1 acting up. You bet. So then FA is going to equal, I'm going to add, these two are negative, I'm going to add them over. So what you're doing, you called up the ramp positive just now, whether you realize it or not. The way you worded that, FA is positive, or up the ramp is positive. So FA is going to equal the force of friction plus FG parallel. And now we can start to plug things in here. I had a discussion with a couple students after class yesterday, and they were like, well, I've forgotten everything. Everything you need for this chapter, there are no surprises. Everything's on the formula sheet. So if you don't remember friction, it's right here. Gravity is right there. Universal gravity is right here. Gravitational field strength is right there. You'll have access to, you have one of these, and you'll have access to this for any unit test you do. So force of friction is equal to mu Fn. So we've got an applied force is going to equal mu Fn plus Fg perpendicular, but Fn is just equal to what? What's the normal force equal to? Fg perpendicular. These two are equal and opposite. So we're going to have, that's going to be equal to mu times Fg perpendicular times, or plus rather, Fg parallel. So we can start plugging stuff in here. Oh, mu was 0.18. So I'm going to get 0.18. Fg perpendicular, we had an expression for. This angle right here, the top one, is equal to this the angle of the incline. So this is going to be 25 degrees here. And Fg perpendicular is beside this angle. So which of the two expressions do we use for Fg perpendicular? The sine one or the cosine one? One of them's Fg cos theta, one of them's Fg sine theta. If the perpendicular one is beside the angle, which one do we use for it? Cosine. Because beside is also adjacent, same word, or same meaning. So this is going to be mu, 0.18. Fg perpendicular is adjacent to the angle, so that's just going to be Fg cos 25 plus, this is opposite, that's going to be Fg sine 25. So keep going, it's going to be 125 times the cosine of 25 plus 125 times the sine of 25. You don't have to do a bunch of stuff in your head, just keep writing, making little changes every time. Yes, it takes up more space, but I give you lots of space. The trees are already dead, use them. Help them fulfill their life's purpose. Well, one of their life's purposes. The paper has been recycled. Use it. And so now we just punch this in our calculator. I really hope the answer is 73.2-ish. 0.18 times 125 times the cosine of 25, close the bracket, plus 125 times the sine of 25, 73.21920793. We're good. Does that make sense, Brad? Yeah. And then 8 and 9 bring in kinematics in a way that I did not do an example for. Brad, you said the wheels fell off for the last 3. So pick one, 8 or 9. Fluffy the cat is sliding down and it asks you to determine the time it takes Fluffy to reach the bottom, or the trucker loses his brakes going up one of those runaway roads that you see off the side of the highway, and we want to know if the runway is long enough. Which one do you want me to do? You want Fluffy the cat? Okay. More space. Okay, question number 8. Fluffy the cat slides freely down the long porcelain cat slide into the Beverly Hills pet pool. Okay. Let's make this big-ish. Here is our cat. Cat's just basically a box. What else do we know about this whole thing? Incline, 18 degrees. Coefficient of friction between the cat and the incline is 0.1. And we all know the slide is 10 meters long, so the distance from here to here, like this distance is 10 meters. Okay. What else do we want to know? That's it. That's all we get. We don't even know Fluffy's mass. That's okay. So free body diagram, what's acting on Fluffy? Friction's which way? It's going to go up the incline. Because Fluffy's sliding down, friction always opposes motion. Force of friction is up there. You bet. What else is acting on Fluffy? You bet. You bet. We don't know what FG is because we don't know the mass, but we'll call it mg. I'll call it 9.8 m. This is g. This is the m we don't know. And now we can break this thing up into components. There's our FG perpendicular. This is going to be our FG parallel. Fn, and we can. I'll just keep going for the. Oh, actually, today's lesson is shorter-ish. We got time. What else do we want to equate here, Brad, or anybody? Trying to find the time it takes to fall. What are we ultimately looking for here? We're looking for the time it takes to fall down, but what big critical concept do we have to find in the interim? What are the forces going to give us? What's the purpose of pulling out all these forces? So we can find the acceleration. The whole purpose of this portion of the problem right here is to find A. And then it becomes a kinematics problem. Okay, cool. So let's find A. So we can leave the diagram as it is for now, if that's all we have. If we're finding A, F net equals MA, which way do you want to call positive, Brad? Sure. That makes a lot of sense. If we're going down as positive, what's the F net expression going to look like? Equals, yeah. Yeah, equals MA. Okay, cool. FG parallel, force of friction, let's play with that one first. We're going to get FG parallel minus force of friction. If you ever forget, it's on your formula sheet. Force of friction is equal to mu Fn. So FG parallel minus mu Fn equals MA, but Fn, FG parallel minus mu, Fn is just equal to FG perpendicular equals MA. And now I've got these two. I've got FG parallel, FG perpendicular, and that angle there is 18 degrees. So I can just replace FG perpendicular and FG parallel with their expressions related to FG. You can rederive them every time if you want, but if you remember the trig, there are shortcuts to it. FG is the hypotenuse, the perpendicular, these guys meet at right angles. So this side is adjacent, this side is opposite. So to find FG perpendicular, we're going to use cosine. To find FG parallel, we're going to use sine. So the FG parallel is going to be FG sine theta minus mu times FG cos theta equals MA. I replaced parallel and perpendicular with FG sine and FG cos. And I left that mu there. I'm just changing one thing every line as I work my way down. FG is just 9.8 times m. So I'm going to get 9.8 times m times the sine of 18 minus mu is 0.1 times 9.8 m cos 18 equals m times a. And I don't know the mass of Fluffy, but it doesn't matter. It's not a typo. Dwayne's not here to say it again. Brad? Because mass is in each term, I can divide each term by m, you bet. Divide by m, divide by m, divide by m. Cancels there, cancels there, cancels there. So we're going to find that the acceleration is going to be equal to 9.8 times the sine of 18 minus 0.1 times 9.8 times the cosine of 18. It's going to equal a, and a should be, I don't know what that number is. Sine 18 minus 0.1 times 9.8 times the cosine of 18. I found the acceleration to be, it's not the end, so let's put a bunch of decimal places there, 2.0963. And that's going to be meters per second squared down the incline. And so what I'm going to do now is I'm going to take this acceleration, that's the whole point of looking at the forces, and I'm going to go back and look at the kinematics side of this problem. So I'm going to bring it up to here. Kinematics, list what you know. Acceleration is equal to 2.0963 meters per second squared down. VI is what's VI for Fluffy? If they don't tell you, 0. Presumably when you start at the top of a slide, the cat is not moving. What else do we know? We know, what are we looking for? Kale said we're looking for time. What else do we know? We know the distance the cat's going to travel. The cat's going to go down the slope the slope is 10 meters long. So the displacement is 10 meters, the initial velocity is 0, the acceleration is that, we're looking for time. So, based on this information, we go back to our kinematic equations, we're looking for that guy there. D equals VIT plus 1/2 AT squared. VI equals 0, so that term is gone. So D equals 1/2 AT squared. D is equal to 10 times 1/2 times 2.0963 times T squared. I'm going to get 10 divided by half of 2.0963 is equal to T. I want T, so I have to square root that too. So now that's the thing I'm going to have to shove into my calculator. Square root of 10 divided by 0.5 times 2.0963, and I should have closed that bracket. Just to clean it up a little bit. Close that bracket. Boom. Please be. Yes, it is. 3.088789275 seconds equals t. Question 8 says 3.1 seconds. So this rounds. And we're done. Question number 9 plays out very, very similarly. The only difference between question 9 and question 8 is that in 9, the truck is going up the incline, so friction's acting down the incline with FG parallel. So those two are going to act together down the incline to bring that truck to a stop. And then once you find the acceleration, instead of finding t, this is what I tripped you a whole bunch of you guys up on the kinematics test. The question says, if the runoff road is 100 meters long, is it long enough? So 100 is not the distance. You're looking for the distance, and you want to compare that to the 100 meters. You have to find out what the distance actually is. In this case, it should be something like 98.9 meters is the distance the truck actually goes. So the 100-meter runaway road is, in fact, long enough. And you're given an initial velocity of 150 kilometers per hour. So there's going to be a conversion that has to happen there, too. Brad, all that make sense? I am recording all of this, so if there's any comments, questions, concerns, like the video will be here. As you guys go off, should you choose to study, especially the sciences, well, math or the sciences at university, a skill that you want to be able to develop if you can, practice it, is things like predicting the kinds of problems that your teacher could throw at you. One in my third year, I can't remember if it was my third or fourth year, class size at U of V are small, especially in the physics department. We had classes of 10 or 12. So we regularly would spend time with our professors outside of class, whether they would stay in our, like often, especially U of V is a small school, like there was an upper level physics lab. We would stay there, the profs would rotate through, and they would come and they would teach whatever course, and then they would leave and we would stay. The professors all had office hours. It's and offices themselves. It's exactly the opposite to how we have class here. I stay here, you guys rotate. University is the other way. Students stay, teachers can rotate. And so one day after class, my Jeff Chisma, my professor, he's still at U of V. He's an incredible teacher. He sat down with us and we said, okay, Jeff, we have a final exam coming up. What's going to be on it? And he laughed at us. I'm not telling you what's going to be on it. And so we sat down and we just started talking like, okay, so these are the major, and one guy was on the board and the other three of us were talking about, okay, these were the main concepts that we talked about over the course of the semester. These were the main kinds of problems that we looked at. So for this final exam, it's 3 hours long. It's probably going to be this many questions. So you're probably going to do one of these. It would make a lot of sense to do one of these. It would make a lot of sense if you did one of those. And you really are probably going to want to test us, so you're probably going to give us one of these. And he sat there with a straight face until we were done listing on the board what we thought might be on this test. And we were like a day and a half away from the final exam. Maybe 2 days away from the final exam. Not long. And his response to us was, I can't repeat it verbatim because I'm being recorded for YouTube at a public high school, but well F. If I had time, I should remake we nailed it. Every single thing. We sat down and we talked, we discussed. We're like, what's going to be on this thing? What is a good assessment of our knowledge thus far? And we nailed it. Between the four of us, we figured out exactly what questions were going to be on the final. And when the final came, he hadn't changed it. It was exactly what we predicted. So, I have 6 questions here. Some of these are the standard incline questions, but I think we can all agree the inclines, these ones are substantial. They bring in friction. They bring in, we've got FG here, we've got Normal force here, we've got friction here. If I really wanted to give you one question off this page that really put everything together, because I don't have time to give you everything. If I gave you one really good incline question and you had to predict which one it was going to be, what would you guess? Probably a question like 8 or 9. And if you stop to think about it, which one would really, not A, is Dawidoff an ass and is going to out to get me, is, because that's not how I build tests. Sorry, that's not true. I did that once when I had a class of, I had a cheating ring going on, and I was like, how am I going to get these guys? So that one time I built the test that way. The question I'm always going to ask myself is, what is one question I could give you that's going to give you, that is the meatiest, that's going to give you a chance to look at everything? And Brad's right. That's a question like question 8 or question 9. I told you one of these 6 is going to be on your unit test next Wednesday. I'm not going to tell you which. But I would tell you, if I was a betting man, if Brad was a betting man, I love to gamble in high school, he's going to put money on it's going to be either 8 or 9. And I would say that's probably a pretty good bet. It puts everything together. It's inclines, it's friction, it's kinematics, it's everything. Those are good questions. So do with that information what you will. This is kind of like peak difficulty for this unit. The last 3 lessons we're going to look at are all about momentum. Mathematically, momentum's a lot easier. The only trick with momentum that we're going to look at is the positives and negatives. It's the same stuff that's been tricking you guys up since chapter 1. But as far as like really looking at the meat and potatoes of some of these concepts, a question like 8 or a question like 9, really good questions. So there's the video if you want to go back and review how I went through it. If you want to go again through it yourself. Practice 9. Make sure you're able to do 8. It'll be okay. Okay. For something entirely different. Everything up till now has been dynamics. Everything up, it's been forces. I looked at a bunch of different kinds of forces. We talked about springs and friction and normal. Gravity, 2 different ways. One when you're really high up and one when you're really quite close to the surface of the planet. We changed G. We talked about gravitational field strength. We've looked at all of these different concepts. And really, this is enough to have a chapter test made up of just this. But momentum is a concept that we need to look at in 11, and it's 3 lessons long, and then the unit is done. It doesn't make a lot of sense, I don't think, for me to give you a data review, forces, and then have a force test, and then 3 days, and then a data review, and then a unit test. I'm trying to save days where I can. Semester 2 is always already shorter than semester 1. So what we do is we take momentum and we tack it on to the end of dynamics. Momentum is easier. Momentum, it's a way to make the dynamics test a little less painful. And I'll give you 2 days to review for this thing, and I still won't have to give you 2 test days. So we tack momentum on here, even though momentum is radically different. So let's take a look at it. Momentum is language that you guys have thrown around a bunch already. We talked about momentum when we were talking about the concepts related to inertia, and inertia was connected to the object's mass. Inertia was largely, right? An object in motion wants to remain in motion. Object rest wants to stay at rest unless acted on by an outside force. And they want to maintain whatever motion they have. And so the more massive the object is, or the faster moving, or the bigger the change in velocity, the harder it is to change inertia and that kind of thing. Inertia is kind of an airy-fairy, we can talk about it, kind of hand-wavingly concept. There is no real number behind the concepts of inertia. We just know if an object has it or it doesn't by whether or not the object's going to be easy or difficult to stop. Momentum actually allows us to take those concepts, those ideas of inertia, and give it concrete values. I mean, this is just as abstract as anything. Like, if you think about what momentum is, like, how would you, it's not like we have a momentum meter in the car, because momentum is going to change as things change in the car. We have a velocimeter in the car. We call it a speedometer, but it's a velocimeter. Because that's concrete. It's meters per second. It's how far over what time. Momentum's a little bit different, and momentum's a lot more abstract. So any object, any moving object has momentum, and that depends on what? Similar to how I described inertia, the more velocity something has, the more mass something has, the more inertia it has. You can think of inertia as how scary is this thing to stop? So if you have if my son is walking at you, nobody is going to be intimidated by my 2-year-old, unless you're scared of kids, but that's a different story. If Fuge started to march at you, that's a little bit more intimidating. Fuge is a lot more difficult to stop than my 2-year-old. Even if they were walking at you at the same rate, Fuge versus my 2-year-old, Mr. Fujimura is probably 250 pounds. Big man coming at you, even if he's just walking slow, is intimidating. It's hard to understand why sometimes, but it is. And so we can understand that, you know, if your job was just to stop one of the two, you'd probably pick my son, because my son has the smaller mass, even though the two velocities are the same. So we know inertia and now momentum, the thing I'm trying to connect to, is related to the mass of the object. The more massive something is, the more momentum it has. But you can also take something that's really light, something that isn't very big at all, and all of a sudden now it can be quite concerning. There's a conversation I had with my science class. If I brought in a box of, so I've got firearms at home. If I brought in a box of .22 ammunition, and I held it out here and I just started like throwing it at you, would that concern any of you? I mean, forget the fact that I brought a box of ammunition to school. If that was normal, and I'm just throwing 22 bullets at you, is that concerning? As it relates to the damage the 22 bullet could do to you. I'm just tossing it. It's plinking off Lachlan's back. Nothing's happening. They're small. What if, in addition to the box of ammunition, I also brought the 22, and instead of throwing it at you, I loaded it and started popping off 22 rounds? Henry's laughing at the back because that would be wildly concerning, wouldn't that, Henry? You should be deeply concerned if that was the case. But what's the difference? It's the same little piece of metal. What does the second one have that the first one does not? Massive amounts of velocity. So a small object, even though the mass isn't there, a small object moving very, very quickly is as scary to stop as a large object, a very massive object, moving very slowly. The danger to you is still the same. I mean, how it plays out in reality is going to be different. But in both instances, you should be concerned. And so likewise, it's the same hand-waving argument I made with momentum. Sorry, I made with inertia. Momentum is the same. The more mass something has, the more momentum it has, and the more velocity something has, the more momentum it has. You can take a really small object and give it a ton of momentum by cranking up the velocity. You can take a really massive object, and even though it moves slow, it can still have a lot of momentum. Maybe you've seen, there's all sorts of war movies or Band of Brothers HBO show. Perhaps you've seen these things. If I rolled a skateboard towards you and bumped it off your ankle, not overly concerning. But if a tank, for example, was moving at you at the same rate and it decided that it was going to go where you stand, do you have any chance of stopping that thing? No. Even though the velocity is the same, both of them could be crawling towards you at an almost imperceptible rate. The tank with its larger mass is definitely going to squish you. The skateboard will just bump off your leg. And so momentum really is just a combination of these two. Momentum is abstract. We don't have a momentum meter. It's not pretend. It's an abstract concept that we give to objects to help us analyze what's going on with them. And so momentum really is just mass times velocity. That's all it is. Mathematically, super simple. The letter that we give momentum is a letter that gets used a bunch of different ways in physics. It's not the letter M because the other M is right here. Does anyone want to take a guess at the letter we use for momentum? It's close to M. Did you look at the formula sheet? Is that why you're guessing that one? We use P. We use P for a bunch of different things. P is going to be momentum. P is going to be power in the next unit. P is going to be period if we look at waves and optics, which we probably won't have time to do. P is also going to be equal to momentum. So momentum, P, is equal to M times V, where this P is equal to momentum. M is exactly what you expect it to be. V is velocity. It's not actually, for those of you who care about this kind of thing, it's not actually the letter P, but calling it the letter P is the easiest way to look at it. It's actually the Greek letter rho, for those of you who like the Greek alphabet and are interested in this kind of thing. But as far as writing it out, it looks like a P, so we're just going to use P. The Greek letter rho, it's momentum. Mass, as always, measured in kilograms. Velocity, measured in meters per second. So if I'm taking those two values and I'm multiplying them together, what are my units for momentum going to be? If I take kilograms and I multiply them with meters per second, momentum is going to be what? And it's exactly what you think it's going to be. It's just weird to say. Someone fight the weirdness and say the units. Yeah, sorry, was that a hand? It's going to be a kilogram meter per second. So, this box, we're just going to write out everything I basically said at this point. Momentum, we haven't said this yet. What kind of quantity do you think momentum is going to be? Look at the things that make up momentum. Is momentum going to be a scalar or a vector, looking at these two concepts? Mass is mass a scalar or a vector? What's the difference between a vector and a scalar? It's a scalar because scalars have no direction. Weight would be the vector because it's a force. So mass is not a vector, mass is a scalar. Velocity is a vector because velocity depends on the direction in which you're traveling. So if you take a scalar and multiply it by a vector, you're going to get another vector. And so what that means is that momentum is a vector quantity, meaning it adds both a direction and a magnitude. And it's this direction that's going to this is the tricky part with momentum. This is the part where people are going to get tripped up because it's the positives and negatives getting involved. The units are kilogram meters per second, as Sire already said. We can write them another way, which is a little bit interesting. I'll show you what I mean by that. I'm going to go up here. I'm going to zoom in on this kilogram meters per second piece. And just for fun, one of the things that we do in physics is we multiply by the number 1 a lot. It's My professor, it's not a trick, it's a technique. And the only things that are going to change are if you multiply by 1, what 1 are you going to multiply by? And what he kept meaning was that if, here's a bit of an aside. You don't have to write this part down, but you can if you want. Multiply by 1. What does it mean to multiply by 1? Well, I can multiply by 1 and things don't change. Or another way to represent 1 is to say, okay, well, 1 is just equal to something, I don't know, x divided by itself, right? Like anytime you have a fraction where the numerator and the denominator are the same, up to this point in your mathematical career, we look at that and say, oh, this is awesome, because these cancel. Well, why do they cancel? They cancel because a number divided by itself is 1, and multiplying by 1 doesn't change anything, but you can go the other way. And so we're just going to change, we're just going to pick a convenient one to multiply by. I'm going to go to these units, and I'm going to say, okay, well, I want the one that I'm going to multiply by to be seconds over seconds. Again, multiplying by 1 doesn't change anything, but it allows me to reformulate what's going on here, because, well, what is going on here? Then if I multiply both these by seconds and seconds, it's going to change. I can bring these two s's in the denominator together. I'm going to get kilogram meters per second squared, and then another seconds up top. What is this? That's a kilogram. Kilogram is mass. This is meters per second squared. Meters per second squared is a measure of acceleration. So this is a meter, sorry, this is a mass times an acceleration. Mass times acceleration is a force. So this is going to be, these are units of force. But we said at the beginning of our unit on dynamics, we don't like this because kilogram meters per second squared is cumbersome. It's chunky. And so we want to replace that with something more sleek and elegant. So we said, okay, forces are actually going to be measured with what units? What do we measure forces with? Newtons. So I can take this and I can say, well, this is actually, this whole box, I can call a Newton. And that seconds that I multiplied by is still there. So I just multiplied by 1, didn't change anything, and I absorbed this denominator into the other denominator, and it gave me something new. It said, okay, well, then I can convert this. I can say this is actually a Newton. So momentum can be measured as a kilogram meter per second by looking at a mass times a velocity, or momentum is equivalently equal to a Newton times a second. Newton is a force, seconds are time, and so momentum isn't just going to be a mass times a velocity, it's also going to be a force times a time, which is conceptually a little bit weird, but ultimately very cool. We now have two expressions for how to calculate momentum. And if you didn't follow what I just did, really it is okay. I just need you to accept that that's true and be willing to use it. But if you did follow what I did, it's a really quite a cool technique. We do it in physics all the time. What one do you multiply by to give you something that can nicely simplify? So a kilogram meter per second can also be written as Newtons times seconds. Today, I'll do 3 examples for you. All we're going to look at is momentum using this top expression. This is what we're going to look at tomorrow. So, a couple nice easy examples and then you're free to play. We want to calculate the momentum of a 92-ton train traveling at 80 kilometers per hour. Just like kinematics, write down what you know. You don't have to free body diagram this thing quite as aggressively as we did last chapter. Or, sorry, not last chapter, but earlier this chapter. We know the mass, we know the velocity. Mass is 92 tons. How do I take tons and turn it into kilograms? Does anyone know how many tons there are, how many kilograms there are in a ton? Especially when the ton is spelt this way, the British way, the correct way, sire? Nope. It's 1,000. A metric ton is 1,000 kilograms. An imperial ton, like the American ton, is 2,000 pounds. So it's not quite as clean a conversion into kilograms. Okay, so if a ton is 1,000 kilograms, this is just going to be 92,000 kilograms. The velocity we have is 80 kilometers per hour. I don't want 80 kilometers per hour. I want to turn that into a usable unit. I want that to be in meters per second. So how do I go from kilometers per hour into meters per second? Divide by 3.6. So 80 divided by 3.6 is going to be 22.2 repeating. So now if I just want the momentum of the train, I just take those two values and I multiply the thing together. How much momentum does the train have? P is equal to mv. So my mass is going to be 92,000. The velocity is 22.2 repeating. You multiply those two values together and you're going to get 2,044,444 kilogram meters per second. This is why trains are so freaking scary and why you don't want to be on the track when it is also on the track. 2 million of anything is a number that should concern you. We could find out. We could throw Kale back on the scale. We could time him as he's running down the hall. You know what? Kale, do you want to find your momentum? Not really? Does anybody want to find their momentum? How much momentum they have? Is that a thing anyone would like to do? Kai, do you want to find out your momentum?
I'm all right.
You're all right? Okay. Well, then we'll just go with my examples. If anyone wants to volunteer, we can go to the hallway and we can figure out your momentum. It's not hard to do. Okay, if nobody wants to volunteer, let's look at baseballs and bowling balls. Same idea. A baseball has a mass of 0.14 kilograms. It's moving at 35 meters per second. What's the momentum of the baseball? Well, momentum is mass times velocity. This mass is in kilograms. We like that. This velocity is in meters per second. We like that. There's nothing to convert. Just multiply those two things together. 0.14 kilograms times 35 meters per second. That baseball has momentum of, I'll give you the value, 4.9 kilogram meters per second. That is not a large number. But, I mean, that's a quick moving baseball. 35 meters per second is over 100 kilometers per hour. That ball's moving pretty good. What would the velocity, look at part B here, what would the velocity of the bowling ball have to be, or find the velocity at which a bowling ball, mass 7.6 kilograms, would have to have the same momentum as the baseball? So we want to find the velocity this time. So we're going to start with P equals mv. We're given the mass, 7.6 kilograms. V is what we're looking for. And the question says, we want the bowling ball, find the velocity at which the bowling ball would have the same momentum as the baseball. The baseball had 4.9 kilogram meters per second of momentum. So the bowling ball is also going to have 4.9 kilogram meters per second of momentum. How fast does the bowling ball have to move to have the same amount of momentum? Well, I want to solve this thing for V. So because I see this mistake all the time, I want to make sure we're clear on this. How do I isolate V? Divide by 7.6. 4.9 divided by 7.6. V is going to be equal to 0.64 meters per second. So just so we're clear on how fast that is, that's 64 centimeters per second. How big is 64 centimeters? .64 centimeters is that. Okay. So your bowling ball moving this quickly versus a baseball moving at 120 kilometers per hour, same momentum. Questions, comments, concerns on momentum so far? Okay, then I've got one. If not, then I've got one more example for you. This is where the snag comes for momentum. Momentum's a vector, and so it matters which direction you're moving in. We've got a 0.5 kilogram water balloon is being thrown against a wall at 32 meters per second. How someone got the water balloon moving that fast, I don't know. And it's coming to a stop. Now we want to know, what is the change in momentum? Think back to the beginning of kinematics. If I want to find the change in something, what do I have to do? I have to take VF and I have to, well, in this case, it's not VF and VI, it's PF and PI, because I don't want the change in velocity, I want the change in momentum. And what do I have to do with them? A change in a value is equal to, yeah? No. Yeah, I mean, yes, but I want to be really clear on what we're doing. Looking for a change in a value means I take what two states of that value? You said final and initial, and what do I do with them? I subtract them. So a change in something is a final minus an initial, and we gave it a Greek letter, delta, the triangle. So if I want to find the change in momentum of the water balloon, I want to find the final momentum, and I want to take away the initial momentum. So for this one, I'm going to draw a quick picture of what's happening here. We've got a water balloon moving. Here, I give it some speed lines. And it's going to impact with a wall. When it hits the wall, presumably the thing is going to flatten out. Over here, the velocity is 32 meters per second. And here, as Brad already said, the velocity is equal to 0. Before the balloon bursts, we'll assume the mass is the same. That's a whole nother problem. So let's look at this. Change in momentum is equal to momentum final minus momentum initial. So I've got P final, I'll write it out again, minus P initial. Momentum is equal to mass times the velocity. Is the mass changing? No. So I can just write this as the mass with the velocity final minus the mass times the velocity initial. Because the mass isn't changing, it's the velocity that's changing. So P final is going to be M final, V final. P initial is going to be I'll say it again. Momentum final is going to be mass times velocity final. Momentum initial is going to be mass times initial velocity. And so to find the change in momentum, I can just plug in these values. The mass is going to be 0.5, final velocity is 0, minus 0.5, as Brad said it would be, times 32. anything times 0 is 0, but the change in momentum is going to be, the reason, Brad, that I'm going through all of this is to enforce that. Change in momentum is going to be negative because you have an object with momentum and you're taking it away. So we're going to get a value for momentum. It's going to be negative 16 kilogram meters per second, and that negative matters. It reflects that we're taking the momentum of the object away. Be careful not to take the shortcuts until you're really, really comfortable with this stuff. Okay, one more. Instead of a water balloon, because the water balloon is going to hit the wall and probably come to a stop, let's throw a bouncy ball. Bouncy balls are really popular in my house right now. My son loves throwing the bouncy ball as hard as he can, and it bounces all over our kitchen. So let's do it. A 0.5 kilogram bouncy ball. Just so we're clear, on half a kilogram is a pound. This is a 1 pound bouncy ball. Hey, Kai and Kel, almost done. That's a large bouncy ball. A 0.5 kilogram bouncy ball is thrown at 32 meters per second. My son is not throwing this thing. It's bouncing back with the same speed. How does its change in momentum compare to that of the water balloon? So let's draw the picture again. Here's what's actually happening. I've got a ball with speed lines coming in. It's got a VI of 32 meters per second. It's going to hit the wall and bounce back at the same speed. VF over here is going to be 32 meters per second. As soon as you have an object that's moving in two different directions, what do we have to do? We have to make a decision. Which way is positive? It doesn't matter. Which way was positive here? Towards the wall was positive here. So let's just be consistent. Let's call towards the wall positive down here. So let's take a look at what this is going to be. Change in momentum is going to be momentum final minus momentum initial. So this is going to be mass times the velocity final minus the mass times the velocity initially. The mass is going to be 0.5. What's the final velocity? It is not 32 meters per second. You're so close. It is negative 32 meters per second. The negatives are going to screw you guys up every single. If something's going to get you in this little section, it's going to be those minus signs because the math isn't that hard. So 0.5 times the final velocity of negative 32, because we said towards the wall was positive. So a velocity away from the wall needs to be negative. Minus 0.5 times the initial velocity of positive 32. So this is going to be negative 16 minus 16. What's the change in velocity or change in momentum going to be? It's going to be negative 32 kilogram meters per second. The change in momentum is greater if the object is coming back at you. Because instead of bringing the momentum to 0, you're giving it momentum the other way. And I'm done. Comments, questions, concerns on what I've done? Cool. You got 15 minutes, which is more time than you get some other times. Let's practice. Unless Kale wants to go find his momentum. I've got 10 questions here. Do I really want you to do all of them?
Okay.
It's different.
But
It's just different.
if you were comparing.
Take a look at 1, 2, and 3. You can't. It's like comparing football to soccer or to hockey. You can't.
Well, I know, but.
They're all different.
That,
Aerobically,
I don't know.
they're different. Okay, 1, 2, 3. Ooh. You know what? Let's do 4. Oh my gosh. You know what? Forget it. These are all good. They're all tricky ways of changing the language. And I mean, it's not that hard. They're all tricky ways of changing the language to really make sure that you're cool with what's going on here. Do them all. On your market set giver. Let me know how I can help you.
I feel like it's